podcast. This is Mr. White.
And Mr. Sadler.
And today we're going to do a little graphing. So we're going to graph impulse.
So we're going to graph the change in momentum.
Oh, I thought we were going to graph the wasteful spending around the holidays. Let's do the change in momentum thing now. And so I'm just going to go right out of your book. They provide me with a really nice graph. And it's force versus the time. And they've gotten rid of all of the curvy stuff and just giving me a nice rectangle. And according to this graph, from time 2 seconds to 5 seconds, there is a force of 4,000 newtons.
All right.
And so if we were to find the area of this, we would just have to do what, Mr. Sadler?
Base times height.
Yeah, just have to multiply. So the force times the change in time, or the base times the height, would be 4,000
times 3 seconds.
times 3. And so the F delta T, or the change in momentum, would be
12,000
kilogram meters per second. So by finding the area of a force-time graph, you in fact find the impulse, or the change in momentum of the object. The momentum changes because a force has been applied over a time interval. Over 3 seconds, I would say this is like applying the brakes. Okay, that's what this is like. If it was over a very tiny time frame, like tenths of seconds, okay, first of all, the force goes way up, but the momentum change would be exactly the same.
Like hitting a wall.
Like hitting a wall. We could do this a little bit. We could say, look, delta P is 12,000 kilogram meters per second. Let's go ahead and just say the mass of our car, okay, is 1,000 kilograms, and that the final speed of it is 0. How fast was it going? It's a perfectly reasonable thing to do. So the change in P, it is force times time. It's also mass times the change in the velocity. So I work my way through that a little bit. I remember some stuff like the final speed is 0. So the change in momentum is mvi. And so I'm going to do some math. And I'm going to determine that the initial speed is, so 12,000 divided by 1,000 is 12 meters per second. Not sure how I got this negative side. I'm not even sure what to do with it, but I'm not going to just ignore it. It should be negative, I suppose, so it can assign a direction since it's velocity. But there it is. So you can work your way back and find speed. And since you actually knew, now that you know the speed, and you know this took 3 seconds, you can figure out the acceleration.
Correct.
Right? Because acceleration is the change in speed over the time change. So 12 divided by 3 would be negative 4 meters per second squared. So there's all this
kinds of
stuff
things you can do.
is connected, right?
Right.
So what they want you to do, we're going to help you out with one. We're going to give you the rest. Okay. It says create a graph that shows the same momentum change of 12,000 kilogram meters per second where the force is constant, 8,000 newtons. You will have to calculate the corresponding time. So first thing we're going to have to do is some math. 12,000 is our change in momentum. This time the force is known to be 8,000 newtons. We're going to need to know how long this takes place. Delta P is F delta T. Delta P over F is delta T. 12,000 over 8,000 is
0.5.
How convenient? 1.5 seconds. So on my graph, I got force, I got time. Okay, let's say we start this event at 1, which means it stops at 2.5, which means if this was 4,000 on the previous page, then that's 8,000 up there. And so I've got something that looks like this, and I know it's right, because if I were to find the area of it, the area would still be
Exactly the same.
12,000. It asks you to do some of these items. It asks you to deal with variable forces and things like that. But go ahead, do some math, make the graph, connect it all in your brain. That wraps things up for Chapter 3. So signing off, this is Mr. White.
And Mr. Sadler.